So you got a practice final, so that's good news. Then I heard the exam's going to be multiple choice.
The only good news that I've had.
That's good or bad news. The reason why I'm usually not excited about multiple choice exams is that you can't get partial credit on anything. And I'm like the partial credit queen. Like I can get myself some partial credit. With multiple choice questions, they can often have tricky stuff in there. So you have to be a little bit more careful to double check your work if you've got some extra time at the end. I hope you do. Your practice exam is mostly not multiple choice, so it also makes it a little tricky to kind of prepare yourself because you're going to be doing types of questions that can't exactly match up with how she's going to ask you on the exam. Often with multiple choice questions as well, what they'll do is the very common mistake that somebody will make somewhere along the line, like you're almost done, and if you just don't do this one more step, like you'll be wrong. They always put that answer in there as one of the multiple choice answers. And so it makes it so that you can get tripped up if you don't know where to stop on the problem. Now, the good news about multiple choice is one of the answers has to be right. So it's helpful sometimes when you're somebody who's like, my answer, cool, is on there. That makes you feel more confident. That, again, it could be a false sense of comfort, though, if you tend to make the most common mistake. So we still have to be careful to make sure that we don't under-prepare, because I think sometimes people hear multiple choice and they're like, you don't need to be that ready. You still need to be ready because they can trick you. Now, also, your test is Friday, most of you. Yeah. That's rough. The stuff that you're doing right now, she has at the end of the packet. So I'll probably get to those Thursday. So keep learning the stuff she's doing right now. You're doing hypothesis testing with two means now. And there's two different ways you can do the hypothesis testing with two means. It could be two completely separate means. So could be that you're comparing a particular type of math intervention between two different classes. And so maybe in one class, they're actually using like manipulatives and hands-on stuff. And in the other class, they're using a computer program. And if you then want to compare the means between those two classes, they're completely separate groups. So that would be the independent means that we're testing. If we were going to do a pre-test and a post-test for a single group of people, so maybe you want to check people's blood pressures before and after you do a particular intervention, if it's the same person that you're testing twice, that would be the dependent measures or the matched pairs as well. So there's another type of one where you can match up certain pairs of things. And often the matched pair is with yourself. It could be a pre-test, post-test kind of scenario. That's probably the one she's going to go over on Wednesday, tomorrow would be my guess. Anybody not get the sign-in sheet? All right, we're going to go back that direction. Thank you. Okay. What I'm going to do now, I'm going to talk through the top part. The top part of her practice final is definitions, and she posted the solutions to that. So me going over the definitions is silly, but I want to talk through number 4 on here because the definition that she has, like that she's written out as part of the solution, has like words in it that some people might be confused by. So I wanted to kind of talk through this one. So define the terms population, sample, and parameter and statistic. That's all really important stuff to be able to know the difference between those things. She wrote a really nice response. So that's just go through and make sure that you understand all the definitions and stuff. Continuous versus discrete data. We talked a lot about that at the very beginning of the class, and that idea that if you have only very particular numbers that we could choose from, that would be our discrete data, things that we're going to be counting. So discrete data would be things like your shoe sizes. Doesn't mean it has to be whole numbers. Shoe sizes could be that you wear a 7 or a 7.5 or an 8 or an 8.5 or a 9, but you can't wear like a 7.925. There's very specific ones you can count to If it's continuous data, it could be like a 7.925. It could be any tiny little decimal in between things. Now, when we get down to the histograms and bar graphs part, the actual like explanation that they have in the packet, it's fine. But some people were kind of asking me what it meant. So I was going to give you kind of a more like visual on what's the difference between a histogram and a bar graph. It says histograms and bar graphs are both bar charts, but what's a significant difference between the two? So it talked about the difference between numerical data and categorical data with these two things. When you've got a histogram, on the x-axis, you're still going to have numbers down there. So we could talk about like test scores or something down on the bottom. So we could say that maybe like this is from 70 to 80, and then this would be from 80 to 90, and this would be from 90 to 100 on a test. And then along the side would also be numerical data. And that would be like how many people got between 70 and 80. And so maybe right along the side here, you've got like 10 people scored between 70 and 80, and maybe 15 people scored between 80 and 90. On a histogram, you've got numerical data on the x-axis and also numerical data on the y-axis. When we're doing a bar graph, they look kind of similar. I'm drawing bars. With histograms, the numbers, like when we do the actual bars, they tend to be touching each other. With bar graphs, they can be touching each other depending on the computer program that made it, but often there's spaces between the bar graphs. And they both have numerical data on the y-axis, but usually on a bar graph, you have categorical data down here. So this could be maybe we're comparing like people who have different kinds of pets. So maybe this is cats and dogs and hamsters. And so the difference would be if you wanted to say like how many people have cats, you'd say 6 people have cats, and you'd say 10 people have dogs. And over here, you would be saying how many people scored between 70 and 80 on the test, and you'd say 10. We still read them pretty similarly, but the difference is on this x-axis down here, we still have numerical data, and on our x-axis on a bar graph, we tend to have categorical data. So down here on the x-axis, categorical. Okay, so that was what her answer when she was writing it out. She was saying sort of the difference between them is numerical and categorical on one of the axes, but I wanted to give you kind of a visual of that. So that was number 4. Number 5 says we want to compare 2 different groups of students taking Composition 1 in a traditional lecture format and students taking Composition 1 in a distance learning format. We know that the mean score on the research paper is 85 for both groups. What additional information would be provided by knowing the standard deviation? So she's got an answer in there about what a standard deviation tells you. And it's important to be able to explain that in your own words, but if it's a multiple choice exam, what are you really going to be like tested on? She's got some problems further on that do a better explanation of that, so I'm gonna kind of like skip over that one for now, but definitely read through the definitions she has in that section. I don't want to like kill you with the definitions, but read her definition. She did a good job with those explanations. I was told it would be helpful if I actually went through the math part though, because the math stuff, a lot of them only have a numerical answer and not the steps for it. So I was going to jump into that if that works for you guys. Good? Okay. The first one that actually requires us to do some math is number 8. Number 8 says, find the mean and median for each of the 2 samples and then compare the 2 sets of results. So it says a comparison is made between summer electric bills of those who have central air and those who have window units. So central air conditioning for May, June, July, August, and September is here. Window air conditioning for May, June, July, August, and September is here. If we want to find the mean, you guys are good at this, we would add up the numbers and then divide by the number of numbers. So you're literally going to say 32 plus 64 plus 80 plus 90 plus 65. And there's 1, 2, 3, 4, 5 of those numbers. You'll divide that by 5. So I'm going to write mean. And I'm going to put a little C down below it to say it's for the central air conditioning. That's going to be 32 plus 64 plus 80 plus 90 plus 65. And since there's 5 of those numbers, we're going to divide by 5. So if you add those numbers up and you divide by 5, you're going to get 66.2. It's talking about money, so that's $66.20. The median for central air conditioning. To do that, what we need to do is we need to put these numbers in order from smallest to biggest first. So I would put down 32, then 64, then I'd write down 65, then 80, and then 90. And when we want to find a median, if we have an odd number of numbers, it's just the middle number. So because we have 5 numbers here, it's just going to be that middle number there, 65. If we had an even number of numbers, you'd take the 2 middle numbers, you'd add them up and divide by 2. But we only had an odd number of numbers, so it's literally just that middle number there will be 65. Since it's money, it'll be $65. The mean for the window unit, we're going to add up 15 plus 84 plus 99 plus 120 plus 40 and divide it by 5. Which comes out to be 71.6, which since it's money is $71.60. And again, for the median, for the window unit, you're going to start by putting these in order from smallest to biggest. So we're going to put 15, then the 40, then 84, then 99, and finally 120. And again, there's an odd number of them, so we're just going to pick that middle number, 84. Questions on finding mean or median? You can use the percentile method when you have a tiny number of numbers. you're probably not going to want to use the percentile method for it. When I do the next one down in here, there's one where there's a Q1, I think it's on the next page they want you to find. I'm going to show you both ways because you're going to get two different answers depending on if you use the percentile method or you use the traditional method. If there's a small number of numbers, pretty sure she wants you to do it this way. Number 9. This one talks about some definitions. It actually doesn't want you to do any math. The data set below consists of the scores of 15 students on a quiz. For this data set, which measure of variation do you think is more appropriate, the range or the standard deviation? And explain your thinking. Okay. Variation. You've talked about variance, but do you remember what variance means? Or what do we mean when we say variation?
How did this just sigma squared?
That's a symbol, but what does that mean? Like in real words, if a third grader was asking you, what's variation? Or what's variance? What would you tell them? This is what makes statistics so sad. You get to the end and everyone's all caught up in the definitions, but then they're like, I don't know. And like literally, I promise it's not hard. Distribution. It is talking about the distribution of data, but that's not specific enough for a third grader. Because remember, third graders like bug you. They really want to know, but what does it mean? What does it mean? Okay. So I want to read you the numbers. I'm going to be really annoying. I'm going to read you the numbers. These are scores. 90, 90, 91, 91, 89, 90, 89, 91, 91, 90, 60. Oh, 90, 89, 90, 91. What do you notice about those scores?
How close they are to each other versus like what's like not close at all. So it's kind of like standard deviation, but how far are you from like the mean? Because the 60 is definitely going to be an outlier, but everybody else fits within the range of either 19, 91.
So when we're talking about variation, what they're really asking you is how different are these numbers from each other? If this list of numbers didn't have that 60 on there, and I said, how different are these numbers from each other? You'd be like, not different at all, hardly, right? You'd be like, everyone in this class got almost the same score. And if I asked you, what's the range of scores if I get rid of that 60? The range is the biggest number minus the smallest number. The biggest number is 91 and the smallest number is 89. There's like the tiniest range, a range of 2, right? People scored super close together, okay? Now, if I put that 60 back in there and I say, what's the range? That's the biggest number minus the smallest number. Now my range is 31. And so when we're using a measure of variation, variation is saying how different are these scores from each other? These scores, on the whole, are not very different from each other, except for that one outlier sitting over there, that's 60. So what we want is we want a measure that's not going to make that outlier so dang important, because it's just one number in that whole list. And so if we use range for our measure of variation, the range is showing 31. That's hecka different. If you were to do a standard deviation, we're not going to go through the calculation, but standard deviation basically has you find the mean of all these numbers. It would be pretty close to 90. And then you would take each of those numbers and you'd subtract it from that 90, and you'd square those numbers and take the square root. And spoiler alert, the number would come out to be like 1 and some change probably. That 1 and some change standard deviation number is telling you how far away from each other or how far away from the mean are each of those numbers. And each of those numbers are about 1 away from the mean. If you were to calculate the mean of all those things, they're probably going to come out to be around 90. And 91 is about 1 away, and 89 is about 1 away, and 90 is like right there. So it's going to be a pretty small number. So the standard deviation is gonna be a better measure of variation for this one because it's not going to have that 60, that outlier in there, pull on the number so much. Whereas using 31 doesn't tell us a whole lot about how close together all the rest of the numbers are. Is that okay? So standard deviation, it's not exactly this as a definition, like it's not a good definition for it, but it's a good approximate definition for it, is about how far away from the mean are each of the numbers in this set. And if we were to take the mean of all those numbers, they're going to be around 90-ish because most of these numbers are around 90-ish. It's going to get pulled down a little bit by that 60. So maybe it's 89-ish, but it's still pretty close. So the standard deviation would be telling you about how far away are each of those numbers from the mean. And it shouldn't be very big of a number. It should be like 1 and some change maybe. But if you were to do the range is 31. And that doesn't tell us a whole lot about how close together all of the other numbers are. Okay. Next part. I guess I should say, we want the standard deviation. That was the answer for this one. Find the z-score corresponding to the given value and use the z-score to determine whether the value is unusual. Consider a score to be unusual if its z-score is less than -2 or greater than +2. Round the z-score to the nearest 10th if necessary. Okay, we have a formula for z-scores. The formula for the z-score is you take whatever x value they're talking about, we subtract the mean, and we divide by the standard deviation. So in this problem, it says a body temperature of 99.5 degrees Fahrenheit. Given the human body temperatures have a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees. So they're asking you, is it pretty unusual to have a temperature of 99.5? So that 99.5 is the x. The mean is the 98.2. And the standard deviation is 0.62. So 99.5 minus 98.2 divided by 0.62 gives us a z-score of 2.096. It says round to the nearest 10th if necessary, so that would be 2.1 if we round to the nearest 10th. All right, so based on the definition of unusual, it says unusual is a z-score smaller than -2 or bigger than +2. What would we say? Unusual or not? Unusual. Guess what? The definition of a fever is 99.5 or higher.
Oh,
That's why the definition of a fever is 99.5 or higher, because we've decided that a z-score of 2 means that's an unusual body temperature, since our average human body temperature is around 98.6 is usually what we say, but 98.2 is in the range of normal.
also if your body temperature goes up like 2-ish degrees.
So this is considered unusual because it's greater than 2.
Would it still be considered unusual, given the it's at 2 or greater?
The way she wrote that there, it literally just says greater than 2. Now, I don't think she's going to do that to you on the test because 2 is still a pretty unusual score. And if someone said, well, it was 1.99, does that mean it's not unusual? And it'd still be like, well, it's getting close to being unusual. So statistics doesn't usually have those like hard and fast rules necessarily. Normally as a researcher, you'd be having to decide for yourself if something like 1.99 was weird enough for you to say it was weird. So it's kind of like when your little kid comes to you mommy, I don't feel good, and you take their temperature, and their temperature is 99.4. And now you're like, should I keep them home from school? They haven't technically hit the unusual mark, but you're gonna use your best judgment and go, well, my kid doesn't usually pretend to get out of school, so I'm gonna say that's still unusual. Or my kid's a whiner. I don't know. I think they might just be trying to get out of school. You might decide that that's not unusual enough. And so a lot of statistics is you kind of making a call based on judgment. But in this case, the way she wrote it, she literally wrote greater than 2. So I guess if it were a multiple choice question and she put on there it was exactly 2, I'd go, not according to your definition, I guess. Good question. I don't think she's going to do that though. She's not usually that nitpicky. Okay. Which is better, a score of 92 on a test with a mean of 71 and a standard deviation of 15, or a score of 688 on a test that has a mean of 493 and a standard deviation of 150? How would you do this? Those tests are very different tests, right? When we want to compare two things that are using completely different scales, what we do is we change them into a z-score, because that's called standardizing the values. So if you standardize those values and make them both z-scores, then all you have to do is figure out which z-score is bigger, and then you have the answer. So we need to find two z-scores here. So one of the z-scores, we're going to do this 92. So I'm going to call this one z1. Z1 is 92 minus the mean, which is 71, divided by the standard deviation, which is 15. And we're going to go figure out what that z-score is. And then I'm going to do another z-score. I'll call it z2. And we're going to take the 688 and we're going to subtract the mean of 493. And we're going to divide it by the standard deviation of 150. And so what's going to pop out is two z-scores, and we can directly compare z-scores to each other. So 92 minus 71 divided by 15 gives us 1.4. And then 688 minus 493 divided by 150 gives us 1.3. So which score is better? 92 or 688? 1.4 went with the 92. 1.3 went with the 688. The higher score with a z-score was the 1.4. So 92 is the higher score. 92 is the higher score. I'll write that here.
Oh, higher relative position means higher z-score.
Yep. Okay, so again, that's a really important concept from this whole quarter, that you can compare tests that have very different scales. On that test where they got a 92, that test was probably out of 100 points total. On the test that was 688, maybe that test was out of 700 total. So those are very different scales for a test. So how you be like, I don't know who did better. Well, you can't compare them just by looking at them and go, well, 92 versus a 688, you can't compare them like that because they're very different scales. But once you turn them into z-scores, you've made them like standardized, and that's when a z-score is a standardized score. So that means that whichever z-score is higher tells you which one's the better score. So the 1.4 tells us, cool, that 92 is better. Yeah.
So in a situation where we're gonna compare like any two different tests that are different scales, we'll always use the z-score,
Indeed, you will.
just the z-score.
The z-score. Yeah. It doesn't have to be test scores, it has to just be things that you're comparing that are on different scales than each other, things that you would normally say we couldn't compare them. If we can do a z-score, now we can't compare them. Number 12, you're not gonna like. The reason you're not gonna like number 12 is that the answer depends on which method you use. So it says the weights in pounds of 30 newborn babies are listed below. Find Q1. So this is the one I was talking about where I was like, it depends. If you only have a few scores, like 5, like we did earlier, and we were trying to figure out where's the median, just do the normal definition of a median. When you have a lot of numbers, often people prefer to use the percentile formula for the thing. If you do this percentile formula for this, you're going to get a different answer than if you use the traditional definitions of what Q1 is. And they're both correct answers. So because it's a multiple choice exam, this is a little trickier. You're going to maybe not get the answer on your paper that matches with the answer choices. And so you should know that both of them are valid ways to get a Q1. So I'm going to show you both ways so that if you're like, my answer doesn't match, you can go, oh, maybe they use the other method. Okay. So first thing I'm going to do is move this up so that I can write below that list of numbers there. Okay. If we do the percentile method for a Q1, what is the percentile that corresponds to Q1? 25. So we would do 25 over 100 times, and then do you remember what we put inside the parentheses part? N plus 1. What's our N in this problem? 30, because we had 30 newborn babies. So we're going to do 30 plus 1. Okay. So this is going to be 1/4, because 25 over 100 simplifies to 1/4 times 31. So that comes out to be 31 over 4, which if I turn that into a decimal, this is not a whole number. So 31 divided by 4 is going to give you 7.75. Is that the Q1? No. What did I just find when I got the 7.75? I got a position. So on this list of numbers, they're telling me that the Q1 is located at the 7.75 position. Oh, well, we don't have a 7.75 position. Now, first thing that I neglected to say is in order to start this problem, we got to make sure that these numbers are in order from smallest to biggest. They are. They're already in order. Yay. So what I'm going to do, 7.75 is bigger than 7, but smaller than 8. So what you're going to do is you're going to go find the 7th position. And then you're going to add the 8th position. And then you're going to divide whatever you get by 2. We're going to do that to get our Q1. So 7th position, 1, 2, 3, 4, 5, 6, 7, 6.3. Plus the 8th position, that would be 6.4. And we're going to cut that in half. And so when you do 6.3 plus 6.4 divided by 2, you get 6.35. So if that's an answer choice on the test, that is a correct answer to Q1. Okay. But if you look and that's not one of the answer choices, they use the other method. And that's okay. It doesn't mean it's wrong. It's going to be close to this number. Like, it shouldn't be super different. If it's super different, you did something wrong. They should be close. But it's possible this is not the answer choice you'll see. Okay, here's the other definition of a Q1. What's the Q2? It's the halfway point or the median, right? If there are 30 numbers up there, what's the middle number? Oh, this is where people go, oh, wait. If there's 30 of them, that means we have 2 middle numbers, huh? Okay. So do you agree that 15 numbers are gonna be below the middle line and 15 numbers are gonna be above the middle line if I cut this in half. So if I count over to 15 here, let me move this out of the way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this first 7.0, I'm going to put a pink line right after it to say that below that pink line, there's 15 numbers. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Above that pink line, there's also 15 numbers. So I have an equal number of numbers above the pink line and below the pink line. Is that okay? All right. The definition of a Q1 is the median of the lower half of the numbers. If there's only 15 of them, that means I have an odd number of numbers. And so it's going to be the exact middle number of those things. So like if you have 3 numbers, my middle finger, the second number is your middle number, right? So if you have 15 numbers, the middle number is going to be the 8th number. Is that okay? You're like, is that true? I'll circle it and then I'll count for you so that you believe me. 1, 2, 3, 4, 5, 6, 7, 8. 6.4 is the 8th number. So I'm going to circle it and then I'll show you that. That means that below that number, there's 1, 2, 3, 4, 5, 6, 7 numbers. And above that number, there's 1, 2, 3, 4, 5, 6, 7 numbers. So do you agree that that's the middle number? Yeah. So 6.4 is also a Q1 using the other definition for how we find the Q1. So you could say that the Q1 is equal to 6.4, or you could say that the Q1 is equal to 6.35. They're both correct ways of finding the Q1. So either find the exact middle of the number, that's going to be your Q2, and then find the median of the bottom half, that's going to be your Q1, or you do your 25th percentile. When there's a whole lot of numbers, most people use the percentile one. But the actual number that she has listed as the correct answer for this one, she picked 6.4, so she did the traditional method of finding a Q1 for her answer choices. Now, do I think she's saying to you that I think that's what you need to do? No. I think this particular practice exam looks like it's coming from somewhere. It looks like she maybe took it from the textbook or something. And so my guess is if you went to her office hours and you were like, which one do you want? She'd be like, oh, I don't care. Because she taught you both methods in her class. Question.
Do you know if she offered both answers or she just had 6.4 there as the answer?
Somebody emailed me the answers and it just said 6.4. And so when I did that and I had just helped someone with it during office hours this morning and we got 6.35, I went, she has the other one there. But they're both completely valid and I really don't think that she's going to put both of them down and try and trick you. Or if she did, I think she'd mark them both right because they're both technically correct. There was an instructor last quarter who was very into these definitions. And what he did is he never actually put down the correct answer as any of the answer choices, and his were all multiple choice, but he'd never put down the correct answer, and he always asked which one is closest to the correct answer. It was torture. Everyone was like, I did the problem and I got this other answer, and I'd be like, I know, it doesn't mean you're wrong. He like never puts down the actual correct answer. He always puts down the wrong answer and says which one's closest to the right answer. It was torture.
Damn it.
She doesn't do that. So I think you guys are in better shape. Okay. The next part is a definition question. Provide an appropriate response. I love that. Appropriate. Don't be inappropriate, guys. Choose appropriate responses. Okay, suppose that all the values in a data set are converted into z-scores. Okay, we just talked about z-scores, and you can convert things into z-scores and it lets you compare things that are otherwise different scales. Which of the following statements below is true? A, the mean of the z-scores will be 0, and the standard deviation of the z-scores will be the same as the standard deviation of the original data values. B, the mean and the standard deviation of the z-scores will be the same as the mean and standard deviation of the original data values. C, the mean of the z-scores will be 0, and the standard deviation of these z-scores will be 1. D, the mean and the standard deviation of the z-scores will both be 0. Okay. When we talked about z-scores before, and we were drawing pictures of things, always down the middle like this, we would say that z was equal to 0. What was right at z is equal to 0? The mean. So definitely for z-scores, the mean is 0. Okay. When we talk about z-scores, the standard deviation for all of them is 1. Always for z-scores. So we want answer choice C here. Answer choice C.
Normal distribution, 0.
Yep, another way of saying the z distribution is the normal distribution. Z is the normal distribution. All right, now everyone's favorite, probability. Ooh. Okay, find the indicated probability. A die with 8 sides is rolled. Most of our dice have 6 sides, so this is a weird looking die. What is the probability of rolling a number less than 7? Okay, so when they're saying the die with 8 sides is rolled, what they're saying is on one side there's a 1, there's a 2, there's a 3, there's a 4, there's a 5, there's a 6, there's a 7, and there's an 8. They need to be very specific about that because you could have a weird die that only has 4s on it. That would make this problem not work. Okay, we're assuming that each of the sides has a different number from 1 to 8. Okay. What is the probability of rolling a number less than 7? If it's less than 7, is it allowed to be 7? No. So it can be a 1, 2, 3, 4, 5, or a 6. How many total sides were there? That's our denominator. 6 things are going in the numerator. So you're going to put 6 over 8 for this one. Okay. Now 6 over 8, you can simplify this. The answer choice that she gave was 3/4. So we just simplify. Instruction on the next one says, find the indicated complement. The probability that Lewis will pass his statistics test is 0.58 or 58%. What is the probability he'll fail his statistics test? They gave us a hint saying we should find the complement. So we should do 1 minus 0.58. And what's 1 minus 0.58? 0.42. There we go. That's what's on her answer sheet. Okay. The next part. There's a lot happening here. It's not meant to be a hard problem, so bear with me. It says find the indicated probability. The table below describes the smoking habits of a group of asthma sufferers. So we've got men and women. We have non-smokers, occasional smokers, regular smokers, and heavy smokers. And in the table, they also add things up and give you totals along the edges, which is nice because sometimes they give you these tables and there's no totals along the edges. What they're saying is that the total number of people in this table is 1,010. If one of the 1,010 people is randomly selected, find the probability that the person is a man or a heavy smoker. Okay, so I'm going to let M be the person is a man. And I'm gonna let H be the person is a heavy smoker. Okay. Why am I writing those off to the side? Because what I'm gonna do is I'm gonna write a notation down now. Because it says we want to find the probability that the person is a man or a heavy smoker. So I want to put the U symbol in between that union. So I want the probability M or H. Probability of M or H, that's our addition rule. On her formula sheet from midterm 1, your rule is the probability of M plus the probability of H. And do you remember how to finish it? Minus the probability of M and H. Been a minute, huh? Okay. Those are just symbols. Now we got to look in the table to find each of those things. So, probability that the person is a male. In this table, there's 1,010 people total, and 512 of them are men. So the way you write the probability that they're a male is 512 out of the total 1,010. So we're going to put 512 in the numerator. And 1,010 in the denominator. Okay. Our formula's got a plus sign, so I'm going to write the plus sign. Now we want the probability that they're a heavy smoker. Okay, heavy smoker. These are all heavy smokers, and this is in the total column. So 78 out of the 1,010 people are heavy smokers. So we're going to put 78 in the numerator. And 1,010 in the denominator. Then our formula has a minus sign. Now we want the probability that they're male and a heavy smoker. So we need them to be in this row because these are all the men, but specifically we need them to be a heavy smoker. 41 of them out of 1,010. Okay, so our denominator is the same for all of them, so I can go ahead and keep the denominator of 1,010. And now we just need to combine the numerator. So I'm going to do 512 plus the 78 minus the 41. So I got 549. For her answer choice, she didn't have this. She had a decimal. So we're going to do 549 divided by the 1,010. And you get 0.544. And that did match her answer choice. Questions on that one?
I just put like 112 plus 78 minus 41 and then put the answer over 1,010. I got the same answer, so like without you, it's like really good. It's like,
Say that again?
I only put it over 1,010, but I got the same answer.
Oh, yeah. So if the numbers like all have the exact same denominator, you can leave that off until the end.
Okay.
Yeah. Yeah. If they all had a different denominator, that trick doesn't work. But since they were all the same denominator, that works just fine. Yeah. Okay. Next one. Find the indicated probability, express your answer as a simplified fraction unless otherwise noted. So she doesn't want us to do a decimal on this one. Okay. The following table contains data from a study of 2 airlines which fly to small town USA. Okay, so we've got 2 different airlines, Podunk Airlines and Upstate Airlines. Number of flights which were on time is the first column. Number of flights which were late is the second column. So it says, if one of the 87 flights is randomly selected, so at first you're like, where's the 87 come from? In this one, she didn't actually like add the things up for you. So we literally have to do 33 plus 43 plus 6 plus 5, and that adds up to 87. So that's where the 87 is coming from. So they don't always give you all the totals around the edges like they did for the first one. It's okay. If one of the 87 flights is randomly selected, find the probability that the flight selected arrived on time, given that it was an Upstate Airlines flight. Okay, so if it's given that it was an Upstate Airlines flight, that means we're only looking at these numbers right here. Okay, we're not looking at the other numbers. We're only looking at Upstate Airlines. So only looking at Upstate Airlines, what of the 2 numbers is for on time? 43, right? Okay, so 43 is the number that is going to go in your numerator. Okay, now we're only looking at these numbers down here. We're only looking at Upstate Airlines. So how many flights are we looking at total? Yeah, so we have 43 plus 5 more, which is 48. So your fraction is 43 out of 48 for this one. Questions on that one? Definitely like a reading question.
Would we put it in sorry, I was just about to say that, yeah, you don't put it in the notation,
Notation on this one.
like make it up, like given.
So you could, if you wanted to write this in a notation, you'd have to come up with like letters that you would want to use for that particular airline and on time. But in this particular one, again, it's going to be a multiple choice test. So no, you don't.
Oh,
You're just going to find the numbers. If you wanted to, like if you wanted to say, given that it was an Upstate Airlines flight, we could say U was Upstate Airlines if you wanted. And on time, I guess we could say O for on time. Does that make sense? Then we could say the probability that they are on time, given that it's an Upstate Airlines flight. You could write it like that. So probability on time, given that it's Upstate Airlines, would be 43 over 43, 48. But you have to choose which letters stand for what things. But probably that stuff will be easier on a multiple choice test because she's going to be picking that stuff for you most likely if it's a multiple choice exam. So far, there hasn't been a whole lot of math happening. The math is next. All right, so number 18. Find the indicated probability round to the nearest thousandth. How many decimal places is to the thousandth? Ooh, this is a good one. All right. So if I make a decimal 2.359, This place right here is called the 10th place. This place right here is called the 100th place. So this place right here is called the 1000th. So if it says round to the nearest 1000th, it wants 3 decimal places. Okay. A study conducted at a certain college shows that 56% of the school's graduates find a job in their chosen field within a year after graduation. Find the probability that among 6 randomly selected graduates, at least one finds a job in his or her chosen field within a year of graduating. What kind of problem is this? Here's how I would start. What did they give you here? Like letters. If you were gonna give me letters or symbols or whatever, what'd they give you? What's one thing they gave you?
5, 6, 4, 6, and it's 1.
They definitely gave us a P. I heard you say P hat, and that also makes sense because we've recently talked about P hats. This one's not a P hat, it's a P. They also gave us an N. How'd they give us an N? They told us a certain number of people total. What was our N? 6. But then they gave us another number. They gave us a 1, kind of. They didn't really give us a 1 though. They said at least 1. So that means that it could be 1, or it could be 2, or it could be 3, or it could be 4, or it could be 5, or it could be 6. Is this reminding you of anything when I was like, oh, it sucks because you have to do 1 and 2 and 3 and 4 and 5 and 6, or we could do the complement of that thing and only do less than 1, which would mean I only have to find the probability of 0 and then just take the complement of the answer. That was when we did binomial. Good. This is a binomial problem. So here's what's happening. It's binomial because they either get their job in the selected field or they don't. 2 things happen. They either got the job or they didn't. And see how it's kind of hard to tell in this problem? This is binomial. Here's how I got my hits though. There was a percentage, so I know I have a P. Maybe it's a P hat, because sometimes you get a percent later on and it is a P hat, and that could be. For this one, I know it's at least a P of some variety, right? And then I got an N. And then it's saying at least 1 or less than, like when it does that, I immediately go, oh, okay, it's probably a binomial one. Okay. So because this one's a binomial one, you want to figure out, is it better to do what they ask or is it better to do the complement of what they asked? And in this case, if I want to find the probability that X is at least 1, that's greater than or equal to 1, because that's going all the way up to 6, that'd be 1 and 2 and 3 and 4 and 5 and 6. I don't want to do that. That's the same thing as doing 1 minus the probability that X is less than 1. Well, X being less than 1 means it's not even allowed to be 1. It's only allowed to be 0. So you have one thing to calculate. So much better. So when we do this, we're going to do 1 minus the probability that X is less than 1 is going to be us taking the 6 randomly selected graduates, and this is going to be the probability. Let me write one more line here. 1 minus the probability that X is equal to 0 is what that is. So this is going to be 6 choose 0. Okay. Now the P they gave us goes next. They gave us a P of 56%. So we're going to write 0.56 And we're gonna raise it to the power of whatever that bottom number is. It's a 0. Then we always do 1 minus the p right here. 1 minus the p is 1 minus 0.56. What's 1 minus 0.56? 0.44, very good. And we always raise that to the power of the top number minus the bottom number. That's the setup. If it weren't a multiple choice test, you'd probably be getting most of your credit right there, but because it's multiple choice, we're gonna have to actually go further. So now we got to remember a couple things. Okay. When you're doing one of these, this is where you do factorials. So that top number gets an exclamation point after it. That's not really an exclamation point, it's a factorial. You put the bottom number with a factorial, and then you do the top minus the bottom in parentheses, and you put the factorial after it, like that. Now, any number to the 0th power, except for 0, comes out to be 1. So this is the number 1 right here. And then this number right here is going to become 0.44 to the 6th power. Six minus 0 is just 6. So this is going to be 6 factorial. So 6 factorial divided by 6 factorial. That's just 1. You've also got the 0 factorial. The definition of 0 factorial is 1. So this whole number is just 1. So we have 1 minus 1 times 1 times 0.44 raised to the 6th power. So this is all just 0.44 raised to the 6th power. And we're going to add 1 to that. And you get 0.9927, but it said round to the nearest thousandth, so we're going to round it to 3. Okay, so again, what was tricky about this problem was knowing it was a binomial problem to begin with. I knew it was a binomial problem because it had a p in it. It was talking about having a certain number of things and then at least 1 or at least 2 or at least 3, or it could say at most 1, at most 2, at most 3. You could do something like that as well. That's going to be a big hint you're doing a binomial type of problem, because that's where you're going to do those some number choose some other number. And typically the challenge of the problem is figuring out, is it easier to do the problem that they asked or the complement of the problem that they asked? In this case, it was easier to do the complement of the problem that they asked, because the problem that they asked would have required us to do greater than or equal to 1. We would have had to do 1 and 2 and 3 and 4 and 5 and 6. Or alternately, we just have to do x is equal to 0 and subtract that from 1. Next one. A study revealed that 45% of college freshmen are male and 18% of male freshmen earned college credits while still in high school. Find the probability that a randomly chosen college freshman will be male and have earned college credits while still in high school. Binomial? Yes or no? No, this one didn't have a like, we chose this many and it was at least this one, or it was less than this one. It doesn't have any of that in there. It definitely has some ands in there. And it has a hidden given in there. It doesn't have the word given in there, but it says 18% of male freshmen earned college credits while still in high school. So it's actually saying, given that we know the freshman is a male, the probability that they earned credits in high school is 18%. Because college freshmen, we assume we could have more than just male college freshmen, right? So by saying 18% of male college freshmen, they're basically saying, given that we know that they're male, here is the percent of them that earned college credits while they were in high school. So what we need to do is we need to set up a notation for ourselves. I'm going to use let's see, let M be that the freshman is male. And I'm going to let C be the freshman earned college credits. In high school. So then I'm going to write down what they gave us. They said 45% of college freshmen are male. So I'm going to write probability that they're male is 0.45. All right. They also said 18% of male freshmen earned college credits while still in high school. So they're saying, given that they're males, this is the probability that they earn college credits. So given that they're male, the probability that they earn college credits is 18%. So there was a hidden given in there. All right, now the question says, find the probability that a randomly chosen college freshman will be male and have earned college credits while in high school. So what they're asking you for is find the probability of male and that they earn college credits. So male and C. She gave you a formula sheet for midterm 1. And on that formula sheet, the probability of male and C is the probability of male times the probability of C given male. Now, on the actual formula sheet, it has A's and B's, but we would be converting this to C's and M's for ourselves. Here's the good news, we have both of those numbers. So we're just going to multiply those two decimals together. So probability of male is 0.45. Probability of C given M is 0.08. Or sorry, 0.18. And if you multiply those together, 0.545 times 0.18 is 0.081. And that matches for solution. Number 20, kind of a definition question, but kind of not. It says, list the 4 requirements for a binomial distribution. Describe an experiment which is binomial and discuss how the experiment fits each of the 4 requirements. Okay. So Requirements for a binomial distribution. Requirement number 1 is that there's a fixed number of trials. Requirement number 2 is that the trials are independent. Requirement number 3, all of the outcomes of the trials can only have 2 categories. And by that, we mean either this happens or this happens. Only 2 things could happen. And the 4th condition is that the probabilities remain constant for each trial. So it says, give an example and explain how that example fits with all 4 of those requirements. So an example would be you flip a fair coin 10 times. And you count how many times it lands on heads. Okay. So condition number 1 says there's a fixed number of trials. You're only flipping this 10 times. That's a fixed number of trials. If you were to flip the coin infinitely, it wouldn't count as a binomial distribution. So we fixed it at 10 times. You could have fixed it at 100 times. Doesn't matter what that number is there, but it has to be a fixed number. All right, trials are independent. To be independent means the outcome of one of the trials has no effect on the outcome of the other trial. So if you flip a coin and it's heads the first time, and you flip the coin the second time, is it more likely to be tails the second time? No, it's independent. So this is totally independent every single time you flip it. It's equally likely to be heads or tails. Condition 3, the outcome can only be one of 2 things. It's either heads or it's tails. You don't have any other option. And 4th condition, probabilities remain constant for each trial. So just because you flipped it and it was 50-50 that it was heads or tails the first time, doesn't mean that it's 40-60 the next time or 30-70 the next time. It's always 50-50. The probabilities remain constant. So that's what she means by say the 4 conditions and then give an example. Questions on that one? Anna uses the letter X to represent the possible sequences of heads and tails that can be obtained when a coin is flipped 3 times. Okay? The possible sequences together with their probabilities are listed below. So she flipped a coin 3 times, got heads, heads, and heads. And they're saying that the probability that that happened is 1 out of 8 for that particular sequence. And then heads, heads, tails was 1 out of 8 for that sequence. Heads, tails, heads was 1 out of 8 for the probability of that sequence. The question says, is X a random variable? Why or why not? If it is not, which associated variable is a random variable? Give the probability distribution of the associated random variable. Okay. As a definition, a random variable has to be a number. So in this column here under X, that's the random variable X. These things would have to be numbers in order for it to be a random variable. Because those have sequences listed, this is not a random variable. So we would say no, because those sequences are not numbers. Okay. But we could create a random variable if what we did is we decided to say, in the sequence, how many times did we get heads? If we did that, so we could use Y instead. So I'm going to write Y off to the side over here. Make another column. If we let Y be the number of heads, then actually this would now be a random variable. So we put 3 here. And we'd put 2 here. And we'd put 2. And we'd put 1. And we'd put 2. And 1. And 1. And 0. And then what we would do is we would combine together the probabilities of each of these sequences if the random variable like appeared more than once. So for the random variable 3, we'd still have 1/8 total. But for the random variable 2, it appears here, here, and here. So we'd say 1/8 plus 1/8 plus another 1/8. We'd have 3/8 for the random variable 2. So if we made like a separate chart, we'd have Y and then probability of Y. If I put, I guess I'll go in order, 0, 1, 2, and 3. The probability of 0 is still 1/8. The probability of 1 actually appears in 3 places, so you'd have 3/8 for the probability of 1. The probability of 2 also appears in 3 places, so you'd have 3/8. And the probability of 3 only appears in 1 place, so we have 1/8. Sorry, I didn't write those all in a nice form. My fractions are too big. So for 0, we got 1/8. For 1, we have 3/8. For 2, we have 3/8. And for 3, we also have 1/8. All right, I'm gonna do one more and we'll call it good for today. We'll pick up on Thursday. Says explain why the following is a valid probability distribution and then find the mean of this probability distribution. Okay, when we have a probability distribution like this, the first thing you gotta look at is, all right, we got all of our random variables here. These are the probabilities here. For it to be a valid probability distribution, this plus this plus this plus this plus this has to add up to 1. all of those have to add up to 1. So I'm gonna check. I'm gonna do 0.42 plus 0.12 plus 0.34 plus 0.05 plus 0.07. And when I added those all up, I got 1. So this one is a valid probability distribution. They have to add up to 1. They do. So we're good. And then it says find the mean of the given probability distribution. So that's the mu symbol. When we do that, you take this number in the first column and you multiply it by the probability that's associated with it. And then we add. And then we do 1 times the probability associated with this one. And then we add and we do 2 times the probability associated with this one. And then we add 3 times the probability associated with this one. And finally, 4 times the probability associated with the last one. And if we add all those up, we get 1.23. Right. I'll pick up with number 23 on Thursday. If I get solutions written out, I'll post them earlier than that, and then I'll just go over the ones on Thursday.